In this video, we're going to briefly leave aside the technical causes we've already analyzed in detail. Now we're going to approach it from a different perspective, shifting the focus to something that has a direct and very tangible impact on the business: lost production and the associated cost of repair time. This is the point at which operational risk transforms into a real economic loss, and where technical decisions have immediate financial consequences. This is where engineering, economics, and strategy must come together. Let quote S start with a critical statistic. 28% of photovoltaic plants are experiencing more than 120 hours of downtime per year, primarily due to transformer failures. This level of downtime not only means a loss of generated energy, but, in PPA markets, or with binding commitments, translates into contractual penalties and direct loss of revenue. To better understand the origin of these losses, it's worth reviewing the annual failure rates by component. GSU transformers, common in renewable energy plants, have a failure rate of 0.95%, while in conventional substations, this figure drops to 0.53%. However, HV circuit breakers, especially in SF6 systems, reach 2%, reflecting their vulnerability under demanding operating conditions. If we focus on newly built renewable energy plants, the situation is even more delicate. Up to 50% may fail during their first years of operation due to technical immaturity, design errors, or poor installation conditions. These failure rates have a direct correlation with production losses. Transformers account for 45% of these losses, followed by circuit breakers at 25%, protection systems at 15%, and SCADA at 10%. These percentages are not arbitrary. They reflect the operational criticality of each component and clearly establish the priorities for any maintenance strategy. The higher a component's weight in total losses, the more urgent it is to implement specific measures for its control and monitoring. The economic impact of each type of failure is particularly illustrative. A transformer out of service for 30 days in a 100 megawatt plant represents an estimated loss of 2.5 million euros. Meanwhile, a circuit breaker failure with a 1-week shutdown can cost approximately 450,000 euros. It's important to note that these figures do not include regulatory or contractual penalties, but only the opportunity cost of undelivered energy. If we consider power purchase agreements, PPAs, or participation in spot markets, the financial consequences are amplified exponentially with each additional day of downtime. In this context, MTTR, or mean time to repair, becomes a critical variable that often doesn't receive the attention it deserves. While systems like SCADA can be back online in 2 to 8 hours and protection equipment in 4 to 12, circuit breakers require between 8 and 24 hours. But transformers pose the greatest challenge. Their repair can take between 15 and 45 days, in some cases reaching up to 720 hours. This problem is exacerbated when we consider other relevant economic factors. The price of energy ranges between 80 and 120 euros per MWh. The cost of replacing a transformer is between 1.2 and 3.5 million euros, and penalties for unavailability can range from 5% to 15%, not to mention the loss of revenue associated with balance sheet deviations or breaches of PPA contracts. Furthermore, insurers and financiers are beginning to require more rigorous maintenance and reliability metrics as a condition for extending coverage or approving investments, which adds additional pressure on operators. Added to all this are critical thresholds that trigger corrective or regulatory measures. Availability below 95% implies automatic penalties. A shutdown of more than 72 hours requires a formal investigation. 3 failures per year trigger full audits, and if the SAIDI exceeds 2 hours, a report must be issued to the regulator. These metrics apply not only to large plants, but also to medium-sized and small facilities connected to regulated grids, demonstrating the systemic scope of downtime management. In this scenario, mitigation strategies become essential tools. Having a spare transformer on-site, having active 24/7 service contracts, implementing predictive monitoring systems, and designing architectures with redundancy, +1 are all measures that reduce intervention times and minimize the economic impact. Reliability curves help us anticipate risks and make more informed investment decisions. If we reach 98.5%, we can operate without breakdowns. At 96.2%, we will likely face a minor breakdown. But when we drop to 89.7%, the risk of a major breakdown with critical consequences skyrockets. These curves, combined with component-specific criticality analysis, are an essential part of the new risk-based approach that is setting the trend in electrical asset management. In short, the biggest cost is not the failure itself, but the time it takes to resolve it. Therefore, MTTR is just as important as the failure rate itself. A modern operation and maintenance strategy must be based on three pillars: anticipating problems before they occur, responding quickly when they arise, and minimizing the impact on production and revenue at all times. This approach not only improves the plant's profitability, but also strengthens its long-term operational and financial sustainability. After reviewing the key risks and how they can rapidly escalate in costs and downtime, the big question is, how can we anticipate and avoid these scenarios? The answer lies not in a crystal ball, but in advanced monitoring and predictive maintenance. This isn't a fad or a niche technology, but rather a strategic investment with measurable and proven results that directly impact the bottom line and operational resilience of any industrial organization. From a financial perspective, the strongest argument lies in the numbers. Predictive technologies offer an estimated return of between 300 and 500% compared to corrective maintenance. This means that for every euro invested, 3, 5, or even more can be recovered simply by avoiding failures, extending asset life, and reducing operating costs. Most interestingly, these investments typically recover in less than 2 fiscal years, typically between 6 and 18 months. This rapid return on investment makes these solutions strategic tools for any financial management team seeking to maximize efficiency and minimize budget uncertainty. When asked which technologies offer the greatest impact, dissolved gas analysis, DGA, stands out with an effectiveness rate of 95%, closely followed by infrared thermography, 85%, dielectric oil analysis, 80%, and vibration analysis, 75%. However, it's not a matter of choosing one over the other, because these tools don't compete with each other. They complement each other. The true value emerges when they are integrated into a comprehensive early diagnosis system that allows intervention priorities to be established, resources to be allocated intelligently, and the margins of error to be reduced in operational decision-making. Take the case of DGA. This analysis detects the presence of gases, such as hydrogen, methane, ethylene, or carbon monoxide, which are early signs of internal failures in transformers. If we add to this the interpretation using Duval's triangles, we obtain a proactive diagnosis based on parameters such as H2 above 100 ppm, C2H2 above 3 ppm, or CO above 500 ppm. This level of diagnostic granularity allows action to be taken before the failure escalates and affects the entire system, avoiding not only repair costs but also contractual penalties, supply interruptions, and safety risks for technical personnel. Furthermore, infrared thermography allows hot spots in connections, bushings, or insulators to be visualized without the need for physical contact. When the temperature difference across a connection exceeds 5 degrees, this indicates an imminent risk condition that can be anticipated and corrected before it leads to a serious failure. This type of visual analysis can also be used to assess the quality of previous interventions, detect installation problems, and validate the thermal stability of key components. And if we look at the dielectric oil analysis, we find even more useful information. Furans indicate degradation of the insulating paper, while humidity, acidity, and dielectric strength alert us to critical conditions. Values such as humidity above 25 ppm or acidity above 0.15 mg/kg are clear signs of aging or contamination that, if detected early, can be corrected with relatively simple measures before compromising the plant's full functionality. However, for all this information to be useful, the frequency with which samples are taken is also key. DGA analysis can be performed continuously with online sensors or semi-annually if performed in a laboratory. Thermography is recommended quarterly, and complete oil analysis at least once a year. This periodicity allows for active monitoring without compromising operational capacity or incurring excessive costs. Furthermore, these intervals can be dynamically adjusted based on each asset's history, enabling a condition-based maintenance strategy rather than a fixed schedule, which in turn improves resource utilization and reduces unnecessary interventions. Of course, implementing these technologies requires more than just purchasing sensors. They must be integrated with existing SCADA systems, ensuring a cybersecure architecture that protects the data, properly training the technical staff who interpret it, and establishing standard and robust communication protocols. In other words, a smart and well-thought-out implementation that considers not only technical aspects, but also organizational, operational, and cultural aspects. Because technology alone does not generate value if it is not accompanied by aligned processes, skills, and culture. And when we compare monitoring methods, we see that online monitoring has the advantage of offering real-time data, early detection, and automatic alerts, although its initial cost may be higher. Offline monitoring, on the other hand, is more economical and accurate for certain analyses, but it doesn't allow for immediate response to a critical anomaly. The choice between the two depends on the type of asset, the environment, and the company's business model, and in many cases, the optimal approach is a hybrid combination that leverages the best of both worlds: agility in detection and depth in analysis. In terms of results, the tangible benefits are overwhelming. The life cycle of critical assets can be optimized to 40 or 50 years. Unplanned downtime can be reduced by 70 to 85%. Useful life can be extended by 15 to 25%, and total operating costs can be reduced by 30 to 40%. These figures not only justify the investment, but also consolidate a sustainable strategy that improves the company's competitiveness, reduces its exposure to technical and financial risks, and strengthens its reputation with customers, regulators, and shareholders. Ultimately, predictive maintenance should not be viewed as a cost, but as a strategic lever with a return well in excess of 300%. It makes it possible to avoid most catastrophic failures, improves asset availability, and transforms operational uncertainty into technical and financial planning. Most importantly, it fosters a culture of prevention based on data and informed decisions, which makes the difference between reacting to a failure or intelligently anticipating it. In an increasingly demanding and automated industrial environment, where the pressure on efficiency and reliability is at its highest, anticipation is not a competitive advantage, it's a vital necessity.